Okay, so we are now recording, second time. There's no use watching the first recording, of course, so don't even look at the first recording. That was useless. Share the screen, hope it works. Okay, here we are. All right, so I might want to go a little bit faster because I lost 20 minutes, but I think we're going to be okay. So 13.2 and 13.3 for today. So I'm kind of following along with the calendar here. I still think I can do it. Okay, so let's try to keep this for now, 13.2 and 13.3. Next time 13.4, and I'll give you a quiz, most likely on 13.2 material, but maybe something other here. So I'm not going to change the exam date. So even though I may finish 13.4 on Thursday, I'll just go ahead and get started. Remember, I'm still aiming to push the day of the last exam up to maybe 5/13, so we can have 1 day of review before the final exam on the 20th. Okay, so let's keep the exam on Tuesday the 23rd, and that means I'll just get started with 14.1, 14.2, or whatever the case may be. And just like the previous test, I'll try to give you a day to ask questions ahead of time. All right. Okay, so finally, I think we're ready to do some math. So let's pick up where we were. So 13.2. Okay, 25. Find parametric equations for the tangent line to the curve with the given parametric equation at the specified point. Okay, so there's a curve in space. Imagine you're in space and you're going like this. You're at a particular point in space, 1, 0, 1. Okay. Now, what happened in 2 dimensions? In 2 dimensions, right? Way back in Calc 1, you had a curve. Pick a particular point, come up with the equation of the tangent line, right? We're doing the same thing in space now. Okay. Parametrically, we have a space curve defined by x is equal to that, y is equal to that, z equals to that. You come up with a 3-dimensional curve. You're at a particular point, and you want to come up with that tangent, right? So something similar. So we're just doing a lot of similar stuff as Calc 1 and 2, only on a higher plane in 3 dimensions. All right, so here are the equations. Okay, the first thing I want to do is translate this to find a t value. I need to know t because my equations are all in terms of t. Okay, which of these are easiest to solve for t? Probably z. Okay, in other words, I need to find a t so that this comes out to be 1, this comes out to be 0, this comes out to be 1. The easiest one is to look at z, right? You don't want to look at that and that. So e to the negative t is equal to 1. That simply means t is 0. Agree? Okay, so again, I had to solve for t. I don't want to do that, I want to do that. Let's do that. And let's double check. If t is 0, e to the 0 cosine of 0, that's 1. E to the 0 sine of 0 is 0. And e to the 0 is 1. Okay, so it works. Okay, so how do I find a tangent? Derivative. Okay, so I take the derivative of r. And when I take the derivative, I'm taking 3 derivatives, right? So product rule, and chain rule a little bit. Okay, so the derivative of e to the negative t cosine t, first times the derivative of the second, e to the negative t times negative sine t, plus the second function cosine t times the derivative of the first, which is negative e to the negative t cosine t. So the derivative of x is this. Remember, for the direction vector r is x, y, z. So this is x prime, y prime, z prime with respect to t. Okay, derivative of y, same thing, product rule. First, e to the t, negative t times the derivative of the second, derivative of sine t is cosine t, plus second function, sine of t, times the derivative of the first, the derivative of e to the negative t is negative e to the negative t. And then the derivative of e to the negative t is negative e to the negative t. Okay. All right, so that's the derivative at any t, which could stand for time. Now I want, in particular, t equals 0. That's why I had to solve for t first. Okay, so they gave me a point, but it's actually better if they gave me the t. So t is 0, I plug in. Fortunately, that wipes out a lot of stuff. So put a 0, sine of 0 is 0. That's 0. Cosine of 0 is 1. So r prime of 0 is negative 1 for the x component. And for the y component, 0, sine of 0 is 0. 0 there is 1. E to the 0 is 1, so that's 1. and put a 0 there, that's -1. So my tangent vector is -1, 1, -1. Okay, that's the direction vector v. And you're given the point 1, 0, 1. Okay, so r is r0 plus tv by formula. Okay, so the tangent line, I'm not sure why I wrote A here. Why did I write A? No. R. Sorry, that's R. So by formula R is R0 plus TV. Put that in your formula sheet. Okay, so the original position vector, 1, 0, 1, that's just the original point written as a vector, plus a scalar multiple of the direction vector, -1, 1, -1. Okay, so x is equal to 1 minus t, y is 0 plus t, and z is 1 minus t. So there we are. So those are parametric equations for the tangent line. Okay? That's just like what you had in Calc 1. Find the equation of the tangent to the curve, blah, 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 at a given point. Okay? So now we have a space curve. There's something in space. So you have a tangent, right, in space. And these are parametric equations for that tangent. Okay. Okay, 33. So 33, the curves R1 and R2 intersect at the origin. So R1 is t squared t cubed. R2 is sine 2t t. Intersect at the origin. Find their angle of intersection correct to the nearest degree. Okay, so they both come into the origin. Here are the two functions. I messed up here, so ignore that. Come back up. Okay, so these are two space curves. Imagine they're coming in space and they intersect at some point in space. That point happens to be at the origin. Okay, so they're coming in like so. There's an angle between them right here. Okay, so find that angle that's between them, and we know how to do that now. Okay, so first I need to find their tangent vectors. So the derivative of R1 is easy. That's 1, 2t, 3t squared, right? 1, 2t, 3t squared. And the derivative of this is cosine t, cosine of 2t times 2 by the chain root, and 1. Okay, R2 prime. Okay, the language is we take the derivative, but you're really taking 3 derivatives, right? Take the derivative of R1, you're taking 3 derivatives. Give me the derivative of R2, you're doing 3 derivatives. And there we go. And we're at the origin, where R is 0. And by the way, they didn't give it to me, but you can tell. If we're at the origin, that means x, y, and z are 0, t is 0. And this one tells you that t is 0. Okay, so I plug in 0 for each one. So that's 1, 0, 0. Right, plug in 0 there, plug in 0 there. So R prime of 0, R1 prime of 0 is 1, 0, 0. Side note, do you remember what's another name for 1, 0, 0? I, right? It's the vector I. Okay, this one plug in 0. Cosine of 0 is 1. 2 cosine of 0 is 2. And 1 is 1. Okay, so the two tangent vectors that are coming at the origin are 1, 0, 0 and 1, 2, 1. How do I find the angle between them? We have the formula. Cosine of theta is u dot v over norm u norm v. So the cosine of the angle between them is R1 prime dot R2 prime divided by magnitude of R1, magnitude of R2. So dot product, 1 times 1 is 1, 0 times anything is 0, 0 times anything is 0, so 1, divided by magnitude of I is 1, or formally square root of 1 plus nothing plus nothing, and square root of 1 squared plus 2 squared plus 1 squared, 1 plus 4 plus 1 is radical 6. So cosine of theta is 1 over radical 6. Theta is inverse cosine 66 degrees, okay, to the nearest degree. And yeah, I'm picky about that. Some of you noticed that on the test, but if it says round to the nearest degree, you should give me in degrees. Some of you had it in radians, but it specifically asked for degrees. So I took off a little bit for that also. Okay, so if it says rounded to the nearest degree, give it to the nearest degree, not 65.9, but 66 or whatever. Okay. Okay, 35 and 37 are not really that big a deal. Evaluate the integral. So 35, 37, it's pretty much just a review of your integration. We're doing, the language we would say is we are doing an integration, but you're really doing three. You're doing the I component, the J component, or the K component, right? X, Y, Z. Same thing for 37. And they're definite integrals. Okay. So 35, integral from 0 to 2 of ti minus t cubed j plus 3t to the 5th k. And I'll quickly change it back to, without the I, j, and k. Definite integral. So integral of t, 1/2 t squared. Integral of negative t cubed, negative t to the 4th over 4. Integral of 3t to the 5th, 3t to the 6 over 6, which is t to the 6 over 2. This is a definite integral. So remember, for definite integrals, you don't need a plus c, which actually, in this case, would have been c1, c2, and c3. Evaluate from 0 to 2. Well, in each case, when you plug in 0, you get 0. So just plug in a 2. So let's see, 2 squared is 4. Half of 4 is 2. Notice that the animal that comes out is a vector. You're coming out with a vector. Plug in 2. 2 to the 4th is 16. Divided by 4 is 4, so negative 4. And 2 to the 6th is 64. Divided by 2, 32. Okay, so the answer is the vector 2, negative 4, 32. That's all. And then 37, I got lazy. Again, it says I, J, and K. I didn't feel like it. I've already told you, whenever possible, I'm going to avoid writing I, J, and K. I'll just write it, quote unquote, occasionally, right? Just to give us a reminder that it's proper, it's there. Okay. There's nothing wrong with writing I, J, K. I just didn't feel like it. Okay, the only one that's sort of an issue is that one. That's going to be an ln thing. Do you remember how to integrate 1 over t squared plus 1? That was inverse tangent, right? This is a simple U substitution. So a little timeout here. Okay, so little timeout for the z component. Integral of t over t squared plus 1. The derivative of the bottom is the top. So I can do a U substitution, right? Let U equal t squared plus 1. du is 2t dt, which means I introduce a 2 here and a half outside. So that gives me 1/2 integral of 2t dt is du, divided by t squared plus 1 is u. That's 1/2 ln absolute value of u plus c. Okay, u was t squared plus 1, but you don't need the absolute value for t squared plus 1 because t squared plus 1 is already positive. Okay, so whenever you have the absolute value of something which is always positive, or strictly speaking non-negative, take it off. So 1/2 ln t squared plus 1 plus c. Okay, so this little sidebar, this side note, was just to evaluate the antiderivative of this. Okay, so now we're ready. So integral of this is ln absolute t plus 1. This is inverse tangent of t. And now we know this is 1/2 natural log of t squared plus 1. Okay, and again, very, very conveniently, when you plug in 0, all of these are 0, right? If I plug in 0, ln of absolute value of 1 is 1, and ln of 1 is 0. Inverse tangent of 0 is 0, because the tangent of 0 is 0. Switch them around, and you still get 0. And put a 0 here, you're taking ln of 1. ln of 1 is 0, and half of 0 is 0. Okay, so again, the only thing of substance is 1. Okay, so ln 2. Inverse tangent of 1 is pi over 4, because the tangent of pi over 4 is 1, you might recall from trig. And that gives me 1/2 ln 2. So that's the answer to this. So, I mean, this is really just a review of Calc 2, of your integration rules and so forth. Okay. All right, so finally 41, and then I'm done with the section. And yeah, it's not even the end of the first half. So I think I'm sort of caught up. And then I can start 13.3. Okay, so let's see what's going on with 41. 41, find R of t, position vector, if R prime is 2ti plus 3t squared j plus radical tk, and R of 1 is I plus j. So this is going backwards, okay? They're giving you the derivative, find R. So we need an antiderivative, okay? It's not a definite integral, it's an indefinite integral, okay? And R of 1 is I plus j. Okay, so how do you do that? So R prime was given to be 2t, 3t squared, radical t. Now, when I integrate, I'm going to treat this as t to the half, right? This is an indefinite integral. That means you need constants. Integral of 2t is t squared plus c1. Integral of 3t squared is t cubed plus c2. Integral of t to the 1/2 is t to the 3/2 divided by 3/2 means times 2/3 plus c3. Okay, you can't just put c plus c plus c. Okay, within the same problem, if I did that, then you're implying that all the c's have to be the same, which they certainly are not. Okay, so for this indefinite integral, there's 3 parts to it: integrate plus c1, integrate plus c2, integrate plus c3. Okay, now they say R of 1 is I plus j. Okay, another way of thinking of I plus j is 1, 1, 0. Okay, what that now means, in fact, it's better to me if you think of it as 1, 1, 0. Okay, that means if I plug in 1 here, I'm supposed to end up with 1. If I plug in 1 here, I'm supposed to end up with 1. If I plug in 1 here, I'm supposed to end up with 0. So I just do it component by component. Okay, so x component. Okay, plug in 1 right here, right? That's x, y, and z. R is a position vector. Okay. Now, if I just say a general vector like v or a or b, the components do not have to be x, y, and z. But for the position vector labeled as r, okay, it always emanates from the origin, so the components are automatically x, y, and z. Okay, so R of 1, put 1, C1 is equal to 1. Sorry, 1 squared, put a 1 here. 1 plus C1 equals 1, that means C1 is 0. Okay. Remember doing stuff like that in Calc 1? Right, where you have blah, blah, blah plus C. Now you have an initial condition, right? It goes through the point 3, comma, negative 10 or something. Then you plug in to find the value of C. We're just doing that 3 times here, right? Doing that here, here, and here. Okay, now for the Y, plug in 1 there. 1 cubed is 1. So 1 plus C2 is also equal to 1. That also means C2 is 0. And in Z component, plug in 1, I'm supposed to get 0. Okay, so plug in 1 right there. 1 to the 3/2 power is 1. So it says 2/3 plus C3 is equal to 0, which means C is equal to negative 2/3. Okay, so I found the C's. So just put 0 here, 0 here, negative 2/3 here, and we're done. So this is the answer. So R of t is t squared, t cubed, and 2/3 t to the 3/2 minus 2/3, final answer. And we're done. Okay. All right, so I think that is it for 13.2. I was able to finish before the break, even though we had messed in time. So yeah, so I'll give you an introduction to 13.3, and then after a while we'll break. So 13.3, arc length and curvature is the next topic. Okay, so you have a space curve. Okay, so you're going like this in space. Okay, you might want to know what's the arc length. Think back to 2D. Calc 2. We had this formula, right? We have this in Calc 2. Arc length, integral of the square root of dx dt squared plus dy dt squared. Can you guess what's missing? It's kind of obvious, right? If I move it to 3D, just have dz dt squared. So page 862, arc length in 3D. Here it is. Put this on your next cheat sheet. You can have either this one or this one. I think this one's a little bit cleaner. Okay, so you saw this in Calc 2. Square root of dx dt squared plus dy dt squared dt. Just add the z component. dz dt squared dt. Okay, and when you stop and think about it, one way you could think of it is in Calc 2, when you were using this formula, it always was in 3 dimensions, and behind the scenes, z was also 0, and the derivative of 0 with respect to t is 0, so this never showed up. Okay, this is true, but you don't really need it. It's just a curiosity. Okay, r prime, okay, the magnitude. You take the derivative, you take dx dt, dy dt, dz dt, and the magnitude. So, oh yeah, magnitude, square root of that thing squared plus that thing squared plus that thing squared. Okay, so you can write it like that if you wish, because you definitely want that. So we'll be doing that. I do have to mention this. It's a little bit tough to explain, but I think there was only one homework problem involving it. Okay, so I'll just mention in passing. On page 863, you have something called parameterizing a curve with respect to arc length. Parameterize a curve with respect to arc length. ds dt is norm of r prime. Okay. If you multiply both sides by dt, it ends up looking like ds is equal to norm of r prime of t dt. Okay, so in the example that they give you here, this came out to be radical 2. If you multiply both sides by dt and integrate, you have s equals radical 2 dt, and you would make such a substitution. Okay, so I know that's kind of hard to explain. I don't really want to spend too much time on it because, frankly, there aren't that many problems with it. But I'll show it to you when you have that homework problem. But again, you have this ds dt, multiply both sides by dt, and integrate. You would end up with this. S equals radical 2t. If you divide both sides by radical 2, t is equal to s over radical 2. So they substituted that there, and there, and there. Okay, so that way you have a function not in terms of time, but with respect to arc length. Okay, so if you go a certain distance, maybe you don't want it in terms of t. You want to know, okay, if I walk out a certain distance, 5 units, 10 units, or whatever, you can plug that into here and find the position. Okay, I'll show it to you when we get a problem with that. Okay, next thing is curvature. Okay. Curvature can be thought of as, well, how much does a tangent vector change as I move along the curve? Okay. Now, see right over here? Offhand, you would say, okay, that has high curvature. On the other hand, if I have a straight line, you'd say, well, it looks like there's no curvature, right? So now we have a definition of a unit tangent vector already, right? Unit tangent vector is r prime divided by its norm, t of t. Okay. All these things in red are unit tangent vectors, right? So how does a unit tangent vector change as I move along the curve? It might be quite an abrupt change. If it's a line, there's no change at all. Okay. So definition of curvature. This is a definition, but it's pretty much something you're not going to use that much. Okay, the letter we use for curvature is kappa. It's a funny looking K. Kappa, K-A-P-P-A. Sorry, I can't write it right now. It's a Greek letter. You've probably heard of kappa before, like phi beta kappa. So Greek letter kappa, K-A-P-P-A. It's magnitude of dt ds. It's a definition. How does the unit tangent vector change as I move along the curve? So as I move along the curve, how does unit tangent vector change? Okay. You don't actually use this for computation, though. It's not very good for computation. So there's other forms. So here are some of the other forms. So in other words, this is true. I would say don't even put that in your cheat sheet. But how does the unit tangent vector change as I move along the curve? Okay. Right. So they have some stuff here for derivation. So here's one formula you want to put in your cheat sheet. Okay, so kappa of t, kappa stands for curvature. Here's a formula. It's magnitude of t prime divided by magnitude of r prime. Okay, unit tangent vector. Okay, divided by r prime. They're not necessarily the same. Okay, take the derivative of t divided by r prime. Magnitude, magnitude. Okay, just as a side note, they show that the curvature of a circle of radius a is 1 over a. Okay, so they did it. Okay, so if it's a circle of radius a, they did that. They computed r prime. They computed t and t prime. Okay, don't do it. You'll get plenty of examples of doing this later. Okay, so there was kappa. So they figured out capital T, the unit tangent vector, r prime divided by norm of r prime. That's that. And they figured out the magnitude of t prime came out to be 1 over a. Okay, so just a side note, okay, if you have a circle with a very small radius, okay, if I were to draw something, you know, draw something like that, it has high curvature. But if you have a circle of a really big radius, okay, I mean, think of the radius of the circle at the equator, okay, you know, I'm exaggerating even there. You'd say, oh, it's not even curved at all. In fact, don't we even sort of make that assumption, right? When you and I walk anywhere around San Francisco Bay Area or whatever, we pretend it's not curved, okay? We pretend it's flat. Okay? It isn't until you get many, many miles do you start to see the curvature. Okay? I suppose that was the concept when some people many years ago thought that the Earth was flat. You know, before now we got, you know, images from outer space and so on of the Earth being round. But many years ago that wasn't there. Said, well, you know, the Earth is flat. I can't tell it's round, right? And for everyday life, just anywhere in the Bay Area, just going a few miles, we don't think of it as being curved. It isn't until you get to many, 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 many miles you start to see the curvature, right? So the formula is 1 over a. So if you have a very, very small radius, like 0.0001, you know, if you divide by small number, you have a big number. So very big curvature. But if you have a super big number, then this thing approaches 0. Okay. All right, so anyway, we have that. Here's another big one. It looks more complicated, but actually there are some circumstances where this is preferred over this one. You say, how do you know which one to use? Well, they might either tell you, they'll tell you, or if they don't tell you, you can pick either one. But this looks more complicated, but it might be easier in some circumstances than this. Okay, so curvature is magnitude of r prime cross r double prime. You might recall in the previous section, we actually did a problem involving that, and it was to set you up for this, divided by magnitude of r prime cubed. Okay, so here's a formula for curvature. See, cross product gives you a vector, so that's a magnitude. And r prime is a vector, that's also a magnitude. That's cubed. They go over the proof of that. You can look at it or not. That's up to you. I'm just going to present it. Okay. And another formula, if you have a two-dimensional curve, okay. So what do I do if I'm back in two space? Back in x, y equals f of x. Bottom of page 865. Equation 11. You have f of x. So we have a plane curve, y equals f of x, and give you the reason why. But kappa of x is, let's see, absolute value f double prime, right? Over 1 plus f prime of x squared raised to the 3/2 power. Okay, so put that in your cheat sheet. So again, in terms of what you should put in your cheat sheet, equation 9, and page 864, equation 10, equation 11 for plane curve. I'll just say off to the side, for number 11, what if we have a linear function? A linear function looks like mx plus b, right? What's the first derivative of mx plus b? M. What's the second derivative? 0. Which means double prime would be 0, absolute value of 0, 0. So if you have any linear function, the curvature is 0, which goes with our intuition, right? If you have a straight line, well, there's no curve at all, right? And then we divide it by that, that's still going to be 0, as we know. Okay. A lot more definition, and then we'll break. Okay, normal and binormal vectors. Okay, definition of normal vector. Okay, this is something called the TNB plane. Okay, we know the unit tangent vector. Okay, the normal vector is perpendicular to the tangent vector. Okay. Sometimes called the principal unit normal. So n for unit normal is t prime divided by magnitude of t prime. So take the derivative of the tangent vector and divide it by its magnitude. Put that in your formula sheet. And then we have a binormal vector, which is defined to be t cross n. Put that in your formula sheet. Okay, and actually, you can look at this or not. This is more for physics, for you physics people. Okay, there's something called the TNB frame. Okay, it's applied to motions of spacecraft and motions of objects. Okay, so as you move along in space, like a spacecraft, you want something called the TNB frame. So as you're moving, you want the vectors T, N, and B. So we know the tangent vector, okay, normal vector, and binormal vector defined as follows. Okay. And there's a very nice summary of all of this on the bottom of 867. So maybe you just want to look at this and put all of these guys on your formula sheet. Okay, so T of T, unit tangent vector. N of T, unit normal vector. Okay, the binormal vector was defined as T cross N. And then formula for curvature, kappa, dt ds. But you're not going to do any problems involving this. You'll be doing that and that. So magnitude of t prime divided by magnitude of r prime, and norm of r prime cross r double prime divided by norm of r prime cubed. Okay. And finally, we're ready to do problems. Okay, so we'll break, and then we'll do some of these after the break. Okay, so break time. Let me stop share. See what time is it. See, I have 7:04. So how about 10 minutes plus 7:15? Okay, let's start up again at 7:15. All right, and I'll put that in the chat also. Okay, and I will disappear also. All right, folks, let's pick up where we were. So we're going to do some problems in 13.3, and then that'll be it for tonight. Okay, so we have 1 to 5, 13 to 29, except skip 23, and then 47. Okay, and I'll show that to you as normal in case you don't want to get the book and never want to get it. And just okay, so this is page 868. Okay, find the length of the curve. So I do the formula for arc length. And let's see. Okay, and anytime you see the graphing calculator icon, you don't have to do that. That requires a graphing calculator. I'm not making you guys have a graphing calculator, so don't worry about that. Okay. Yeah, arc length. Reparameterized with respect to arc length. Okay, so that's one problem involving that more complicated than I was talking about. Okay. Find unit tangent and normal. Use theorem 10 to find a curvature, so use the formula they gave us. 27, 29, those are plane curves. So use the formula for a plane curve, right? And that. Okay, and how high are we supposed to go up to again? Where's my, this 47 was the highest number, I think. And there's only one problem. Find T, N, and B. Okay. All right, so I'll show you one of each type, as you might guess. Okay, find the length of the curve. So it's a three-dimensional vector, or two-dimensional, but it's probably three-dimensional. And T goes from something to something. Okay. Okay, so number 1, 13.3. R of T is T, 3 cosine T, 3 sine T. This is a curve in space. Okay. A side note, I believe this is going to be a helix. Okay. If you look at 3 cosine T, 3 sine T, that gives you a circle in Y and Z. So imagine on a YZ plane you have a circle and then you just move T. So it's going to go like this and come out at you, or negative, it goes like that. So you end up with a helical structure. Anyway, so arc length, integral from -5 to 5 of dx dt squared plus dy dt squared plus dz dt squared. Okay, so dx dt is 1. So 1 squared. Derivative of 3 cosine t is -3 sine t. You square it. Derivative of 3 sine t is 3 cosine t. You square that. So that's 1 plus 9 sine squared of t plus 9 cosine squared of t. Okay, 9 sine squared of t plus 9 cosine squared of t. If you factor out the 9, you'd have sine squared t plus cosine squared t, which we know to be 1. So it's basically just radical 1 plus 9, which is 10. Radical 10. And it'll go from -5 to 5. 10 radical 10. And by the way, you probably want to get somewhat proficient in this shortcut. Okay. If you have the integral of 1 dt, the answer is just the length of the integral. Okay. So you just have to go 5 minus a -5. That will become very useful later on. Later on, we're going to have so many complicated integrals that you should see if the integral of 1 dt is just the length of the integral. Okay, so think of that as a shortcut. So just whenever I see that, it's just 5 minus a -5. Okay. And maybe if you're not convinced of that, little sidebar here. Integral from a to b of 1 dx is x from a to b, b minus a. In other words, the length of the integral. Right? Integral of 1 dx, integral of 1 is x from a to b, so it's b minus a, which is another way of saying the length of the integral. So quickly, you should be able to quickly say, oh yeah, 5 minus a -5, 10, 10 radical 10. Okay. Now you might say, well, I can always do this. Believe me, when you get these harder integrals later, you don't really want to stop and do something quote unquote easy like this. You should recognize right away and say, oh yeah, length of the integral. Like I'll be using that quite a bit later on. We have these real weird integrals. Okay, number 3, R of t is radical 2t e to the t e to the negative t from 0 to 1. Okay, this is a 3-dimensional object of some sort. All right. So take the derivative of this, square root of 2. You're going to square it. Derivative of e to the t is e to the t. Square that. Derivative of e to the negative t is negative e to the negative t. Square that. Right? Formula is radical dx dt squared plus dy dt squared plus dz dt squared. Okay. It's the complete 3-dimensional analogy to what you had in 2-space. In 2-space, you had this. Okay. It's an extension of the Pythagorean theorem, in essence. Okay, let's see, where was I? I'm going to write this as e to the 2t plus 2, radical 2 squared is 2, and this is e to the negative 2t. Okay, believe it or not, this is e to the t plus e to the negative t squared, which is, I'm sure, the reason why Mr. Stewart, author of the book, gave us this problem. So it comes out nice. If you're not convinced of that, square this back out, right? This is like a plus b squared. A plus b squared, we know, is a squared plus 2ab plus b squared. So e to the t squared is that. E to the negative t squared is that. And what about 2ab? 2 times that times that. What's e to the t times e to the negative t? Well, I'm supposed to add the exponents. That would be e to the 0. E to the 0 is 1. So it's 2 times 1, or 2. So it works. And you can see the result. I have a square root of a square. Just take it off. Very easy now. E to the t plus e to the negative t. All right, then I integrate. Integral of e to the t is itself. Integral of e to the negative t is negative e to the negative t from 0 to 1. Okay, plug in 1. E to the 1 minus e to the negative 1. Minus plug in 0. E to the 0 is 1. That e to the 0 is also 1, so it's 1 minus 1, which is 0. Cross that out. Final answer is e to the 1 minus e to the negative 1. Or you can just say e minus e to the negative 1. That's fine. Okay, then 13 and even 15, I believe. Find the arc length function for the curve measured from the point P in the direction of increasing t, and then reparameterize the curve with respect to arc length starting from the point P, and find the point 4 units along the curve in the direction of increasing t from P. Okay, so what are they talking about here? Right, so we're starting there. Okay, if we're starting there, what's my t value? Easiest one is look at this. Okay, that's x, has to be 4. That's y, has to be 1. That's z, has to be 3. Well, t is 1. Put a 1 there, that gives you 4. Put a 1 there, that gives you 1. Put a 1 there, that gives you 3. So t is equal to 1. Okay, now what's all this stuff? So here's what we do. So I have this. So first I find ds dt, which is the magnitude of r prime of t. And if you want to put that in your formula sheet, you may. Maybe I forgot to say that, sorry. There we go. Number 7 there on page 863. ds dt is magnitude of r prime of t. Sorry, maybe I said you don't have to, but I take it back. It looks like we actually do want it for this type of problem. Okay, so that shouldn't be too bad. The derivative of this is -1. Derivative of this is 4. Derivative of this is 3. So dx dt squared plus dy dt squared plus dz dt squared. So 1 plus 16 plus 9 is radical 26. Okay, so ds dt is radical 26. Okay, that means s of t is radical 26 times, since we're at t equals 1, parentheses t minus 1 is where we're at. Okay, the reason for the t minus 1 is because if you plug in 1, s is 0. That's what you want in this particular case. Starting from this point, you hadn't gone anywhere at t equals 1. So radical 26 parentheses t minus 1. Okay, a little bit of simple algebra says t is equal to s over radical 26 plus 1. So solve for t, divide by radical 26, add 1. So here's t as a function of s. So that means r as a function of s, r of t of s. Okay, so all I'm doing is right there and right there and right there. Every time I see t, write this funny thing. So 4, whoops, yeah. Okay, so r is 4 minus s over radical 26. That's like 4 minus t, right? 4s over radical 26 plus 1. And 3s over radical 26 plus 3. I'm just plugging in this thing here, here, and here, cleaning up the algebra, and that's what I get. Okay. The reason why that's nice is because now after s units, so not as a function of time, but as a function of distance, okay, if I've gone so many units away, what point am I at? So if I'm on this ride, if I'm on this roller coaster, rather than saying at what particular time, at time t equals 17 seconds, where am I? You might want to say, okay, if I lay out 4 units of track, if I'm going along this track, where am I? Okay, so s equals 4 units. Okay, then I just plug in a 4 there, put a 4 right there. 4 minus 4 over radical 26. Put a 4 right there. 4 times 4 is 16. 16 over radical 26 plus 1. And put a 4 right there. 3 times 4 is 12. 12 over radical 26 plus 3. Okay. So instead of a function of time, it might be useful to say, if I go so much track at a distance of so many units, 4 units, where am I at? Okay. So we have the function in terms of t. So at a particular time, I can be at a location. But how about as a function of the amount of track that I've let out? Okay. So when you start, you plug in 0, 0, 0, you're at 4, 1, 3. Perfect. Okay. But I've let out 4 units of track. So you plug in 4, that's where I'm at. So 4 units on this roller coaster, I'm here. Okay. If I've laid out 75 feet of track on this roller coaster, now where am I at, so to speak? Okay. Okay, and then 15 is like that, and then that's the only other one that's like that. So let me show you the setup for 15. Okay, 15. Suppose you start at the point 0, 0, 3 and move 5 units along the curve. X equals 3 sine t, y equals 4t, z is 3 cosine t in the positive direction. Where are you now? So instead of giving me a time, okay, you're on this graph, which happens to look like a helix also. Okay, that and that. If I only look at x and z, those are parametric equations for a circle. And then you move in the y direction. So if you have a circle and then move in the y direction like so, you end up with a helix. Okay, so if I walk 5 units along the helix, starting from here, what's my new position? Okay. Okay, so where am I at? I lost my place here. Okay. And by the way, that's t equals 0. You can tell if you plug in 0, the easiest one to look at is this one, right? Y coordinate is 0, 4t is 0, t is 0. Okay, so first I find r prime. Derivative 3 sine t, 3 cosine t. Derivative 4t is 4. Derivative 3 cosine t is negative 3 sine t. Now, what is the magnitude of r prime? So square root of this thing squared plus this thing squared plus this thing squared. So 9 cosine squared t plus 16 plus 9 sine squared of t. 9 cosine squared plus 9 sine squared is 9. 9 plus 16 is 25, so 5. So that means ds dt is 5, okay, which means s is equal to 5t, or t is equal to s over 5. Okay, if you have a hard time seeing this, if you ds dt equals 5, means ds is 5 dt, and if you integrate both sides, then s is equal to 5t. Maybe I should have said that ahead of time. Okay, sorry about this. I got my paper a little wet. It looks like. Okay, so t is s over 5. So what that means is now right here and right here, I can change t to s over 5. So as a function of distance, I can, distance along the track, distance along the helix, I can tell you where I'm at. Okay, so in this particular case, it said you go 5 units. So I plug in 5, put a 5 there, 5 there, 5 there. So here's the location on the track. 3 sine of 5 over 5 is 1. Put a 5 there and you get 4. And put a 5 there, 3 cosine of 1. Okay, so rather than giving me a time, I can give you a distance along the track. So we're starting at the point, where'd it go? 0, 0, 3 along this curve. If you walk 5 units along this roller coaster, where are you at? Here, 3 sine of 1, 4, 3 cosine of 1. Okay. So that's that. And raise it up so you can see it a little bit better. Okay. All right, so now we have some problems involving unit tangent vector, curvature, and stuff like that. Finding unit tangent and unit normal vectors t and n. Use formula 9 to find the curvature. Okay, formula 9 and theorem 10 to find the curvature. So formula 9, use that. And then later on it says use theorem 10. All right. So we're finding curvatures of functions now. Okay. So 17 and 19 are like that. Try some of those. Okay, so 17, r of t is given to be t, 3 cosine t, 3 sine t. So the unit tangent vector, by definition, is r prime divided by magnitude of r prime. So derivative of this, derivative of t is 1. Derivative of 3 cosine t is negative 3 sine t. Derivative of 3 sine t is 3 cosine t. And then divided by its norm, magnitude, length. So square root of 1 squared plus 9 sine squared t plus 9 cosine squared t. And this is getting to be an old friend by now. We know that that's 9, right? 9 sine squared t plus 9 cosine squared, that's 9. 1 plus 9 is 10. So 1 negative 3 sine t, 3 cosine t divided by radical 10. Okay, that's unit tangent vector t. Okay, unit normal vector, by definition, is t prime divided by magnitude of t prime. Okay, I think it's easier not to include the radical 10. Okay, remember, if you have a constant times a function, the derivative is the constant times the derivative of the function. So I'll just factor out the 1 over radical 10. You're allowed to do that. Rather than carrying the radical 10 everywhere, just factor out the 1 over radical 10, and then differentiate all of these guys. So derivative of 1 is 0. Derivative of that is negative 3 cosine t. Derivative of that is negative 3 sine t. And I divide that by 1 over radical 10. times square root of 0 plus 9 cosine squared t plus 9 sine squared t. Okay, these just cancel out. Okay, so a unit vector would be 0, negative cosine t, negative sine t. Okay, this is going to be 3, right? 9 cosine squared plus 9 sine squared is radical 9, that's 3. These cancel out. Divide that by 3, divide by 3, and we have this. And by the way, isn't this a unit vector? This squared is 0. This squared is cosine squared. This squared is sine squared. Add them all up and you get 1. And the square root of 1 is 1. Okay, so unit tangent vector, unit normal vector. Okay. Kappa, magnitude of t prime divided by r prime of t by formula. Okay, so magnitude of t prime, okay, t prime was that. So magnitude of 1 over radical 10, 0, negative 3 cosine t, 3 sine t. Okay, we've seen this several times already. That's 3, right? That's going to be square root of 0 plus 9 cosine squared plus 9 sine squared, square root of 9, 3. So 3 over radical 10. That's magnitude of t prime. Magnitude of r prime. Okay, so we did r prime back here somewhere, or did we? Okay, we did. So r prime is 1. Oh, here we are. 1, negative 3 sine t, 3 cosine t. So what's the magnitude of this? Square root of 1 plus 9, there it is again, recurring theme. 1 squared plus 3 sine squared, 9 sine squared plus 9 cosine squared. And so again, that comes out to be 9. So radical 1 plus 9 or radical 10. Okay, so kappa is this thing, norm of t prime, 3 over radical 10, divided by norm of r prime, radical 10. So it's 3 over radical 10 divided by radical 10. Okay. And do you remember there's a rule in algebra that if you have something that looks like that, you can slide that radical 10 with this one? Okay, so then you have radical 10 times radical 10, or 10 in the bottom, 3 tenths. Okay. Or you can think of this as 3 over radical 10 times 1 over radical 10, and then radical 10 times radical 10 is 10. Okay, so that's another way you can convince yourself of that one. Okay, never mind about that one. I didn't want to do that. Okay, 21. Use theorem 10 to find a curvature. So that's the one that involves cross products. So R of t is t cubed j plus t squared k. Notice there's no I component. No I component means it's 0. So I'm using that other formula. Okay, so R of t is 0, t cubed, t squared. So R prime, 0, 3t squared, 2t. R double prime, 0, 6t, 2. I need the cross product. So R prime cross R double prime. IJK, 0, 3t squared, 2t, 0, 6t, 2. So I is going to be that minus that, 6t squared minus 12t squared, minus j, nothing minus nothing, plus k, nothing minus nothing. So negative 6t squared I. What's the magnitude of R prime cross R double prime? So the magnitude of negative 6t squared is 6t squared. Okay, and then I need the magnitude of R prime. So magnitude of r prime is the square root of 0 squared plus 3t squared, 9t to the fourth, plus 2t squared, 4t squared. So finally, I have what I want. And I just throw it into this guy now. That one. Kappa is equal to the one furthest to the right. Magnitude of r prime cross r double prime divided by magnitude of r prime cubed. So magnitude of r prime cross r double prime is 6t squared divided by 9t to the fourth plus 4t squared raised to the 3/2 power. Okay, this whole thing is raised to the half, right? So if you cube it, it's raised to the 3/2. So that's what it should look like. Okay. And I'll do 25 also. Check something in the chat real quickly. Okay, names of formulas. Well, we didn't really give names of the formulas. If you talk about these guys here. So unit tangent vector, capital T, unit normal vector. B is binormal. So tangent, normal, and binormal. And kappa is for curvature, if that's what you mean by that. Okay. Okay, 25. Find the curvature of t squared, t cubed at the point 1, 1, 1. And if we're at 1, 1, 1, that means t is equal to 1. Easiest to tell from the x coordinate. So this is a space curve. Okay, goes through the origin, you can tell. So, you know, looks like whatever it looks like. You're at the point 1, 1, 1. What's the curvature there? What's considered the curvature? Okay. So by formula, I need r prime. That's easy. Derivative 1, 2t, 3t squared. You see we're taking one derivative, but you're actually taking 3. Okay. R double prime, 0, 2, 6t. Find the cross product. ijk, 1, 2t, 3t squared, 0, 2, 6. Okay, so for I, it's 6t squared. Let's see, where am I? Sorry, 12t squared. 12t squared minus 6t squared is 6t squared. Okay. J is the negative of 6t minus nothing, or negative 6t. And k is 2 minus 0, so 2. So 6t squared, negative 6t, 2. What is the magnitude of the cross product? So magnitude of r prime cross r double prime is the square root of this thing squared plus this thing squared plus this thing squared. So that's going to be radical 36t to the fourth plus 36t squared plus 4. Then I need the magnitude of r prime. So magnitude of r prime is the square root of 1 squared, 1, plus 2t squared, 4t squared, plus 3t squared squared, 9t to the fourth. Okay, so kappa is the magnitude of the cross product by formula. So that's this stuff, square root of 36t to the fourth plus 36t squared plus 4, divided by this thing cubed, magnitude of r prime cubed, radical 1 plus 4t squared plus 9t to the fourth cubed. Oh, this is better if I raise it up maybe. Okay. So again, I'm using this guy, the one furthest to the right. And we've used the other one too. I've used this one here also. All right, now where is it at this particular point at 1, 1, 1? I plug in t as 1. So put a 1, 1, 1, 1. So that's basically 36 plus 36 plus 4, which is radical 76. 1 plus 4 plus 9 is 14. Radical 14 cubed is 14 radical 14. Okay, a little bit of algebra. 76 is 4 times 19. Take out the 4, 2 radical 19 divided by 14 radical 14. So final answer is radical 19 divided by 7 radical 14. Okay, that's considered the curvature of this curve. Where'd it go? Yeah, of this curve, t squared t cubed at the point 1, 1, 1. That's a curvature. Just plug it in. Okay. All right. Okay, what time is it? We're fine. Probably don't want to go too much longer. And by the way, 13.4 is not really that long a section. It's not really that hard. Okay, so I think I'll be able to finish that in plenty of time. But I do have to remember I have to give you time to do a quiz next time also. But anyway, what's next is curvature of plane curves. So back in 2 dimensions. Okay, x to the 4th, x e to the x or whatever. How do you find the curvature of a 2-dimensional object? Then I have to use this one. Okay. So 29. So the function was x e to the x. Okay, so first derivative, product rule. First times derivative of the second, x e to the x, plus second function e to the x times derivative of the first, which is 1. Factor out the e to the x plus 1 e to the x. F double prime, product rule. First, x plus 1 times the derivative of the second, which is e to the x, plus the second function, e to the x, times the derivative of the first, but the derivative of x plus 1 is just 1. Factor out the e to the x, you have x plus 1, or x plus 2. Okay, so function, first derivative, second derivative. So this time, what's kappa? Okay, so by formula again, the top absolute value of the second derivative. So absolute value of this, e to the x is always positive, right? So I can take that out of the absolute value. So absolute value of x plus 2. And divided by this mess, which you can then just leave. It goes on the bottom, aim it right, 1 plus derivative squared all to the 3/2 power. Not very nice in general, but that's the way it goes. So there it is, 1 plus f prime squared, whole thing to the 3/2 power. And just stop there. Just leave it alone. That's about it. Okay, problem's finished, but just a little side note. Can you tell on this graph, x e to the x, there's a point with no curvature. Take a look at the top. A fraction is equal to 0 when the numerator is 0. E to the x is never 0. Where is this equal to 0? X equals -2, right? If you look back over here at -2, if you put -2 here, -2 plus 2 is 0, that's the second derivative. That's at an inflection point. Okay. So you might recall if you have a curve that has an inflection point, like here, that seems to be the most linear, so to speak. So right there, there would be no curve at all. Kind of makes sense. Okay. Or just take a normal sine or cosine curve, right? Take inflection points. That looks like an inflection point. Okay. Wouldn't you say here at these inflection points, it looks more linearly, right? Compared to here, it looks like the tangent would be more like a straight line, i.e. curvature of 0. If that was extra, you don't have to do any homework problems involving it, but just thought it, go a little bit extra. Okay. All right, so that is that. I'm just about done, folks. And in case you're wondering about skipping 23, I show you a little bit of my 23. It came out so bad I decided to throw it out. I mean, it can be done, but it was really, really, really messy. Okay. So showed you 29, 47, we're finished. So even though I messed up the first 20 minutes, it looks like we can still finish early, folks. Okay, so after I do 47, if you have any questions, feel free to bring it up. Otherwise, we'll just go ahead and end. Okay, so 47, find it. Yeah, that's the only one where they ask you to find T, N, and B. Find the vectors T, N, and B at the given point. So R of T is T squared 2/3 T cubed T at the point 1, 2/3 1. Okay, so what is the T value? It's probably easy to look at the Z component. T is 1. So T is equal to 1. And quick double check, if you plug in 1 for all the others, it works. Plug in 1 for X, you get 1. Plug in 1 for Y, you get 2/3, 2/3 1 cubed. And T is 1, okay? Okay, so R prime, that's easy, 2T, 2T squared, 1. T of T is unit tangent vector, is this thing divided by its magnitude. So 2T squared, 1 divided by square root of this thing squared plus this thing squared plus this thing squared. Okay, I changed the order. I'm going to write that first. 4T to the 4th plus 4T squared plus 1. And I'm sure Mr. Stewart made it this way. Okay, it turns out that this is 2T squared plus 1 quantity squared. Very nice. Which means just divide all of these by 2T squared plus 1. So the unit tangent vector T of T, okay, in case you're wondering, capital T is for tangent vector, little t is time. So 2T divided by 2T squared plus 1, 2T squared divided by 2T squared plus 1, 1 over 2T squared plus 1. Okay, now we know that T is 1, little t is 1. So I plug in 1. Put a 1 there and there, that gives you 2/3. Put a 1 there and there, 2/3. Put a 1 there and there, you get 1/3. So the unit tangent vector is 2/3, 2/3, 1/3. Now, what gets a little bit messy is to differentiate this. Okay? So I break it up into components. I need to differentiate capital T. So that looks like it's going to be a quotient rule. This one can actually be done with an algebra trick. The trick is that these two are almost the same, 2T squared, 2T squared plus 1. The trick, rather than doing the quotient rule, is to make them the same and then you compensate. I'll show you what I mean by that. This one, you might recall, you'd rather not do the quotient rule. It's easier to think of this as 2T squared plus 1 raised to the -1 power. That's better. Okay, well, let me do the quotient rule for this one. Okay, x is that, dx dt. So bottom times derivative of the top, 2T squared plus 1 times 2, minus the top, 2T, times the derivative of the bottom, which is 4T, all over 2T squared plus 1 squared, quotient rule. Very messy. Then I plug in 1. I don't even bother to clean it up. I'll just plug it in. It cleans up by itself. All right, so if you plug in 1, That's 3 times 2, which is 6, minus 2 times 4, which is 8, divided by 3 squared root of 9, so negative 2/9. That's x prime of 1. For y, and this is kind of nice, rather than differentiating 2t squared over 2t squared plus 1, here's the trick. Add 1 and then subtract 1 in the numerator. So it's 2t squared plus 1 minus 1. So, in other words, that's what I had, right? 2t squared divided by 2t squared plus 1. And now I'm adding 0 plus 1 minus 1. That's a minus sign there. The reason why I do that is now this right here is 1. 2t squared plus 1 divided by 2t squared plus 1. That's 1. And it's very easy to differentiate 1, right? That's 0. And then I have minus 1 over 2t squared plus 1, which I'm writing as negative 2t squared plus 1 to the negative 1 power. That makes it a lot easier rather than doing the quotient rule. Okay, so dy dt, derivative of 1 is 0, so it's gone. Negative 1 times negative 1 is positive 1. 2t squared plus 1 to the negative 2 times 4t by the chain rule. So 4t divided by 2t squared plus 1 squared. Yeah, so we're reviewing a lot of stuff. We're reviewing product rule, quotient rule, chain rule, all that good stuff, right? And now I plug in 1, 4/9. Plug in 1 there, 4. Plug in 1, 2 times 1 plus 1 is 3. 3 squared is 9, 4/9. Okay, then z. Differentiate this. Treat that as 2t squared plus 1 to the negative 1 power. Okay, so the derivative dz dt is negative 2t squared plus 1 to the negative 2 times 4t by the chain rule. Negative 4t over 2t squared plus 1 squared. Clean up the algebra. Then once again, I plug in 1. Negative 4 over 9. Negative 4/9. Okay. So I took the derivative of this, now make it a unit vector. So what did I come up with? I had negative 2/9, 4/9, negative 4/9. So normal vector at 1, negative 2/9, 4/9, negative 4/9. Okay, one more time. The unit normal vector the one in the middle there, n of t, which I'm trying to find a unit normal vector, the one that looks like capital N, t prime divided by its magnitude. Okay, so I got t prime was this, right? Derivative of x came out to be negative 2/9. Derivative of y came out to be 4/9. Raise it up there. And the derivative of z came out to be negative 4/9. And divided by its magnitude, it looks messy, but it's actually going to come out very nice, believe it or not. Okay. If you square this, that's 4 over 81. That's 16 over 81. That's 16 over 81. Add these up, it's 36 over 81. The square root of 36 over 81 is 4/9. Okay, so I'm dividing by 4/9, which is the same as multiplying by 9/4. Sorry, this is 9/4. Okay, so this is 4/9, right? Divide by 4/9, multiply by 9/4. Okay. Well, if we divide by 9/4, all of these guys cancel out here. Okay. It's almost like you're trading the denominators from 9. Okay, they're all gone, and I have a 4 instead. Okay. So anyway, it comes out to be negative 1/3, 2/3, negative 2/3. I do it the right way. No, I did that wrong. 6/9. Yeah, my bad. This should be a 6. 36 over 81, 6 over 9, right, sorry. Yes, I could make that 3 over 2, but it's more convenient to leave it as a 9, because then all these 9s cancel out. I'm just swapping a 9 for a 6, essentially. That's what I meant to say. Yeah, this is equal to 6 over 9. Yes, it's 2/3, but by leaving it as 9, 6, if I multiply 9 over 6, I'd cancel all these out and just make them all 6s. So negative 2, 6 is negative 1/3. 4 over 6 is 2/3. Negative 4 over 6 is negative 2/3. Okay, so I finally got it. Okay, so unit tangent vector, 2/3, 2/3, 1/3. Unit normal vector, negative 1/3, 2/3, negative 2/3. And finally, the binomial vector, B, by definition, is T cross N. That one, B is T cross N. Okay, and once I do this, I'm done. 8:05, yeah, we caught up okay, even though I messed up the first 20 minutes. Okay, so I'll be done in a minute or so. So if you have any questions, you can go ahead and ask it, unmute yourself or put it in the chat. Otherwise, we're done. Okay, and then, yeah, I'm right on par. I'll be able to mark off 13.3 and keep the schedule. Yeah, right here. So then I'll do 13.4 next time. Okay. So B, by definition, is T cross N. So T was 2/3, 2/3, 1/3. N was that, negative 1/3, 2/3, negative 2/3. Okay. So I, that minus that is negative 4/9 minus 2/9 is negative 6/9. Minus J, that times that is negative 4/9. That times that is minus a minus 1/9 plus 1/9. And then K, 4/9 minus a minus 2/9, 4/9 plus 2/9. Okay, so negative 2/3, negative 1/3 or 1/3, and 6 over 9, 2/3. Okay, so there we go. So this is the vector B. And there we go. Okay, and I'm done, folks. So if you have any questions, you can ask them now. Either unmute yourself or put it in the chat. Otherwise, we can call it a night. So next time I'll give you a quiz. Probably just section 2 is what I'm leaning more toward. Okay, again, frankly, it doesn't really matter. I don't have to tell you ahead of time because you get to use your book notes and talk about it end of class. And so very low pressure, in my opinion. Okay, anything else? Otherwise, we'll quit. Okay, I see nothing and hear nothing, so we will quit. All right, that'll do it for tonight, folks. So everybody have a good night, and we'll see you next time. Okay, all right, good night.
Thank you, Professor.
Thank you.
Thank you.
Good night, Mr. Hom.
Thank you. Good night.